lectures about p-adic groups.
Thanks so much, and thanks to Rebecca Belevin for helping me prepare this talk. So, period rings are a nightmare, but but everything that is in their content is suggested by the classical story over the complex numbers. So let's begin with that story. So let's suppose x over c is a smooth, proper scheme, or a variety. All right, so let's talk about that comparison theorem between étale and de Rham cohomology. So on the one hand, you've got the cohomology of x with coefficients in z. When there's no decoration there, it just means singular. This, when I tensor it with c, there's a de Rham isomorphism relating this thing to the de Rham cohomology of x over c. What does it do? So if you've got a differential form here, or a class of a differential form, it goes to, well, elements here are functions of cycles. So if I've got an n cycle, this takes the cycle to the integral over the cycle of the differential form. Okay. In the situation where x actually comes from a variety over a number field, such as q, then we have a vector space over the complex numbers which has two rational bases. So, well, let me just rewrite the above as follows. So x, z, tensor c is isomorphic to n. Okay. Okay, so one can make sense of a de Rham cohomology group of x with coefficients in q. Oh, let me tensor this with c, and then these two guys compare. So we've got, well, on the one hand, a z module, on the other hand, this rational vector space. Tensor them to c, and they become isomorphic. So we have a complex vector space with two different sets of bases corresponding to the two rational models. The matrix, which relates one basis to another, is the matrix of periods. So the periods are the complex numbers attached to such a variety, given by basically those integrals. So here's an example. Or rather, it's a non-example, because I'm going to talk about the multiplicative group over Q, which is not proper, but just bear with me. So, of course, okay, so. All right, so there's one cycle just going around the circle. So GM is just C star. And then the de Rham over Q. All right, so there's one differential form. It's just dx over x. Okay. And the period is what you get when you integrate one over the other. For x. So that's 2 pi I. So that's the single period of the multiplicative group. Okay. All right. Now, we have to venture out of the situation of varieties over the complex numbers or over the rationals. What happens to this group here when x is no longer, with x is over kind of just some general field? So if x is a variety over any field, okay, well, we still have a de Rham cohomology group, although its definition is, as a purely algebraic thing, is a little more complicated. So I'll just say it can give a purely algebraic definition. Of the de Rham cohomology groups, x over k. They end up being k vector spaces. And, well, it sort of mimics what you do in the analytic situation. I mean, you start with the de Rham complex like this. Here we have the sheaf of functions on x, and here we have the sheaf of one forms. And so on. So this is a complex of sheaves on x, complex of sheaves of OX modules. And then to get this set of groups out of it, you have to do something called take the hypercohomology of this. Or that is, it's a construction in the derived category. So I don't need the specifics of this, but I just want to mention that it is done this way. So if you take the hypercohomology of this, you get these spaces Hn de Rham of x over k. And then what structure comes with these things? Well, you always have a certain spectral sequence which relates these Hodge groups to the de Rham cohomology. Okay. Okay. So at least if k has characteristic 0, then this de Rham cohomology group comes with some structure. It comes with a filtration. Well, I'll just call it this. So, I'll just write it this way. Has a filtration for which, okay. I'm doing this to minimize the notation here. So whenever I have a graded vector space, I can talk, a filtered vector space, I can always talk about the corresponding graded space. And this is going to be this direct sum of Hn minus p x omega p x over k. Okay, so this p goes over z like so. All right, so there's a filtration of Hn de Rham by subspaces such that the successive quotients are these spaces right here. Now, in the situation of a variety over the complex numbers, that's a little extra structure you have, and that structure is enough to split the gradation. It means that this is actually equal to the direct sum of these guys. But for a general field of characteristic 0, this is the best you get. This is what you get from the degeneration of the Hodge de Rham spectral sequence on page 1. Okay. All right, so de Rham cohomology groups for varieties over characteristic 0 fields have that much structure. So in the p-adic world, let's see what we can do here. So I mentioned a theorem last time by Faltings. Actually, well, okay. I'm about to mention a bunch of theorems that apply to any finite extension of QP, but I want to keep notation to a minimum, so everything is just over QP. Forget about K, it's just over QP. So let's suppose X over QP is smooth and proper. And let C be the completion of an algebraic closure of QP. Okay. So the theorem of Faltings, which I alluded to, which generalized a theorem of Tate from last time, was this. So it's basically that you can read off the Hodge filtration just from the Galois representation on the étale cohomology. All right. So it's going to be, this. All right, base change to QP bar. This is QP. This thing is a p-adic representation of the Galois group of QP. Let's tensor it with C. And then it breaks up into a direct sum. I and Z, Hn minus I. X over QP. Tensor C minus I. Okay. So when you tensor this kind of vector space, this Galois representation with C, you get a C vector space with a semilinear action of Galois. And that's very simple, it turns out. There's no Galois action here, so you just get a sum of vector spaces of the form C negative I. So it's quite strong. Great. So this is an isomorphism as GQP representations over the field C. So this is Faltings' theorem. Now, I want to think of this as having something to do with periods, right? Now here we have this isomorphism between two cohomology groups tensored with C, And I said that the transition matrix from one to the other, those were the periods. Okay, what are the periods in this context? Well, there's that direct sum there messing everything up. So I just want to rephrase this isomorphism so that it looks, to get a statement which looks more like this statement, okay? All right, so I introduce a ring of periods which are sort of bigger than C. So okay, so this is the first of our period rings. It stands for Hodge-Tate, HT, because this is the Hodge-Tate decomposition. Hodge because it's a Hodge decomposition, and Tate because it generalizes what Tate did for abelian varieties. Okay? So let's let B Hodge-Tate be the following graded ring. So it's the direct sum over I and Z of Ci. That's it. Okay. So this is a ring with the obvious ring structure. Ci times Cj is Ci plus j. Great. As a ring, it's just polynomials in one variable, but you would join the inverse of that variable. So this has the structure of a graded ring, of course. It's a graded QP algebra, and it has a GQP action. Yeah. Then what happens when I take Galois invariance here? Well, you get some behavior which you expect of all these sorts of p-adic period rings. When you take GQP invariance, you must always get QP, the field you start with. So why is that true? Well, you get this sort of thing. So I mentioned a result last time, which is that the cohomology of the Ci is always trivial, except in the case where it's the zeroth cohomology and I equals 0. So you just get CQP here, CGQP here, which is just QP. So like that. Okay. All right. Now, yeah. All right, so what do we get here? Okay. So I wanted something like this, but what I'll do is I'll just replace C with this BHT. Here's my giant eraser. Okay. All right, so when I take Hn, et al., xQP bar, coefficients in QP, and I tensor with BHT. All right, so BHT is the direct sum over, let's say, J and Z of Hn, xQP, B, tensor Cj. All right, but we know from Falting's theorem how this works, so that just shifts the minus I into a J minus I. Okay. So this is now a direct sum over all I and J and Z. Did I do that right? No, it's J minus I, isn't it? Good. All right. Everything okay? What did I do? C. I forgot the C. Thank you. You're doing this. In the sum, what I want to do is change the variable. I want to replace J with J plus I. Why don't I just do that? So that's great. Okay. And then what do we have here? All right. Let me just rewrite this as tensor C J. Okay. But now this direct sum, I mean, this part has to do with only I, and this only to do with J. And on the left, we have sum over I and Z of Hn minus I, x over QP, tensor. And then on the right, just the direct sum of the Cj's, which is just B Hodge-Tate. Now this thing that I've bracketed on the left, so this is just the direct sum of all of these cohomology spaces, and that direct sum, let's just call it the Hodge cohomology. So it's the sum of all of the graded pieces of de Rham cohomology. So I'll just call this thing H Hodge. Just call it X over QP. So this QP vector space is defined to be just this direct sum, tensor B H Tate. Good. All right, so what we have now is two cohomology spaces, one the étale with its Galois representation, and the other the Hodge with its gradation. This does not have a GQP action, and up there does not have a gradation. But when you tensor it with this ring which has both, the two structures become equal. All right, so this is the whole formalism behind period rings. So BHT is the ring containing the periods, at least in this context of where we only care about Hodge cohomology. Okay. If I make the following definition, if I let D Hodge Tate evaluated on a p-adic representation of GQP, and I define it to be, well, what I do is I take V and I tensor it with B Hodge Tate. Tensor with V, and then take GQP invariance. Okay, this is the general thing. Anything labeled D in this subject, it inputs a p-adic representation, it tensors it with the appropriate period ring, and then it takes Galois invariance. That's the pattern every time. If I do it with this particular representation Hn étale of X, what I get is just the Hodge cohomology. So D Hodge Tate of Hn étale. Okay, H Hodge. There we go. All right. So this sets the stage for the general pattern. There is going to be some functor from p-adic representations of GQP to QP vector spaces, possibly with some additional structure. And from geometry, I mean, if your V comes from geometry like this, it should output the corresponding object on the de Rham side of things. Okay. All right. So, okay. All right, so you could input any V into this functor DHT that you like, but of course you may get 0, even if the thing that you started with was not 0. For instance, you could take some power of the cyclotomic character, which is not an integral power, and then what you get is just 0. So we need some nice category of Galois representations which work well with respect to this. So I make a definition, which is that a Galois representation V is Hodge Tate. Well, there's many equivalent definitions, but this is the simplest one. When you do this functor to it, the dimension of the QP vector space that results should just be the same as the dimension of the V you started with. Okay. So in other words, so a priori you have that this is at most this, but you want to have it equality. Okay. So in particular, it can't be 0 if the thing you started with was not 0. All right. Okay. All right. So this is very good. So we've got some functor from a big class of Galois representations into just graded vector spaces, which, when V comes from geometry, recovers the pieces of the Hodge filtration. But the category that this thing goes into is just graded vector spaces. That category isn't awfully rich. So it doesn't remember much about the original Galois representation. So, okay, so there's a sort of cascade of refinements of this idea. And the next one would be not D Hodge Tate, but rather D de Rham. Okay, so that's what we talk about next. In this talk, we talk about de Rham and Chris, and that's all I have time for. Okay, so let's mimic this. Hodge Tate with de Rham. So the de Rham cohomology of a variety had this filtration, of which the graded pieces was the Hodge cohomology. So what we do is we want to replace the ring of periods B Hodge Tate with something else. And B Hodge Tate won't be a direct sum. It won't be a graded algebra, but rather it'll be a filtered algebra. So we seek a filtered QP algebra B de Rham so that Well, when I take my Hn étal of x with QP coefficients, and tensor it with BDR, and then take Galois invariance, this should be the nth de Rham cohomology. And on either side of this, so there's a filtration here, there's a filtration here, and this isomorphism should respect the filtration. So this is as filtered QP vector spaces. Okay. All right, so what should it be? Well, given that the Hodge filtration of Hn de Rham, when you take the graded bit of it, you get this the Hodge cohomology. We should have when you take the graded ring associated to the filtered algebra B de Rham, you should just get B Hodge Tate. Okay. So what did I call? So we have some filtration here. There's a fill. Okay. So it goes like this. Let's put fill 0 in the middle. Fill 1's here. It's going to be an ideal. Fill negative 1's here. And the union of all of them is going to be B de Rham. Okay. So the 0th graded piece of this would be fill 0 mod fill 1. And that should be the 0th graded piece of Hodge Tate, B Hodge Tate, which is just C. So whatever B de Rham is, it should admit a map to C whose kernel should be the ideal, whatever fill 0 is. It should admit a map to C whose kernel is fill 1. All right. So at the very least, this should be true. We give a special name to the 0th graded piece. That's just called B de Rham plus. It's one of the many appearances the symbol plus makes in this field. But generally, when there's a plus, there's always a version without the plus, which means you inverted something. Okay.
Plus means there are fewer things.
Plus means there are fewer things, always. No, I don't believe there are any exceptions to that. That the thing with the plus is always a submodule of the thing without. Unlike dagger, which is usually bigger than the thing without the dagger. This is a plus sign. See? Okay. Great. So we're looking for some huge ring which admits C as a quotient. Okay. So I like to think of this as a bit of an analogy with if you had, instead of C, you had some perfect field K of characteristic P. Okay. Well, the big ring is then the Witt vector ring. The kernel of that would be just everything that's visible by P. And then the corresponding filtered ring would be the ring you get when you invert P. This thing is filtered by the lattice W of K. And somehow this thing is analogous to all of B de Rham. Okay. All right, so yeah, okay. So I mean, instead of K, we have C here. We can't go ahead and take the Witt vectors of C because C has characteristic 0. I mean, we can, but we won't get anything. We'll get a nightmare. So what we can do, though, well, we already did something like it in the last lecture, which is that we passed to the corresponding characteristic P field. So last time, I talked about a field K infinity, and I passed to a certain field E of characteristic P, and that was the perfect field, no, the imperfect field of norms. There was also an E tilde, which was the perfect field of norms. So I want to do something similar here. So, okay. So starting from C, I want to pass to a field. Now, I'd like to call the field C, and I'm going to call it C tilt, because in the kind of brave new world of perfectoid spaces, this is the notation for that. But you have to be aware that the thing could also be called E tilde. There's a terrible clash of notations that pervades the entire subject. You just have to know both. It's like a foreign language with irregular verbs. You just have to know everything.
So
And that's right, it's also called, thank you, it's also called R, right? Thank you. Great, okay. What is the thing? All right, so this is a valued field. Let me tell you its ring of integers. It follows the same pattern as last time. So you take OC mod P, that's now a ring in characteristic P with lots of nilpotents. You take the inverse limit under the Frobenius maps. Right. Okay, and now you get, well, this is actually a valuation ring. It's a domain, and you can take its fraction field, and that fraction field is C tilde. You just have to invert one non-unit. Yeah. And then you can go ahead and take the Witt vectors of that thing. And that's a ring in characteristic 0. That ring admits a map to OC, which I talked about last time. This was called, this is usually called theta. Okay. And now this is beginning to look a little bit like the situation that we want. Once I invert P, I'll get some ring which maps to C. In fact, surjects onto it. But actually what I want is to get a complete DVR out of this. So I've got to do some kind of localization. All right, so now I'm ready to define. Right. Actually, sorry, one more note. From last time, we discovered that the kernel of this map theta is principal. It's just generated by a single element, which I called omega. That's going to help us. Okay. Now I can define what B de Rham plus is. So B de Rham plus is the completion of OC tilt, invert P mod the kernel of this map theta to the n. Okay, so n. All right, so it is the completion of this ring W of OC tilt 1 on P, which is a ring in characteristic 0. It's the completion of that with respect to the ideal, which is the kernel of this map theta. Okay. And wonderful. So this, as promised, this should really have a filtration. And what is that filtration? Well, it's just filtered by this ideal kernel theta. So the map theta extends to a map like this. The kernel is still principal. Well, the element omega suffices. Yeah, okay. And then we just define B de Rham to be the fraction field of this guy. Okay. Good. So this is actually a field. Okay, wonderful. All right, so this is a nice ring of periods for a very broad class of varieties over QP. And what Faltings actually proved, rather than the theorem that I'm erasing, is a stronger theorem about smooth, proper varieties over QP. Well, before I state that, I want to connect this story to So what's the connection to periods here? Okay, maybe best to work out the example, like from the top of the hour with the multiplicative group. Okay. All right, so let's consider GM as a variety over QP. All right, and let's consider its first cohomology with coefficients in ZP. So in the complex world, the thing had a topology, and you could just take its cohomology with Z coefficients, and that was just like, its homology is just one cycle around the origin. We expect this thing to be one-dimensional too, but what you get using Kummer theory is that this is just ZP minus 1, ZP Tate twist minus 1. Okay. So this is as a GQP representation. So it's one-dimensional, and the Galois group acts on it by the inverse to the cyclotomic character. Okay. So, okay, well, all right, so I better offer some explanation there. Remember when I said that the étale cohomology of an elliptic curve, say, or an abelian variety with ZP coefficients, well, it's not quite the Tate module, but it's dual to it. So this is like TP of E dual. Yeah. Think of this as like dual to the Tate module of the multiplicative group. Works rather the same way. The Tate module of the multiplicative group would be like the inverse limit. Yeah, I can write it this way. TP GM is like the inverse limit of the torsion. The p power torsion, though, is just mu p to the n. And so that's just ZP1. And that's what the homology is. The cohomology will be dual, so that's why you get this. Okay. And then de Rham, well, de Rham works the same way as before. Being algebraic, you really get the same result no matter what you do. So again, yeah. QP dx over x, where x is the variable in GM. Great. So this thing has a filtration, and what can I say about it? So this equals its fill1, but not its fill2. So the fill2 part is 0. The reason is that fill1 inside of H upper 1, de Rham, is supposed to be the holomorphic 1 forms, and dx over x is indeed a holomorphic 1 form. There aren't, yeah, okay. There are no 0, 1 forms, so what am I doing here? Yeah, okay, that's good. So, okay. Great. So what we expect to happen next is a comparison between the cohomology, the étale cohomology, and the de Rham cohomology once we tensor with B de Rham. So we expect, okay, so the pattern is like this. You take your cohomology, which carries its GQP action. You tensor with B de Rham. And then you take GQP invariance. And then this you expect, whenever you do this to something which comes from geometry, from an étale cohomology group, you get the same thing, but with H1 de Rham. GM over QP. All right. So in fact, we get isomorphism of graded QP vector spaces this way. Oh, sorry, filtered QP vector spaces this way. And the element dx over x here lies in the fill1 part of this guy. So it should lie in the fill1 part of this guy. So it should correspond to some element here, which I'm going to call T. Okay. So I mean, we have some basis element here, but it should come at, it tensor T. So T is some element of B de Rham here. And where does B de Rham live? So, okay, so it's not quite fixed by GQP, but when you tensor it with ZP minus 1, it is fixed by GQP. That means that, well, it has to live here, just because it lives here. And also, since I said that dx over x lived inside of fill1, this has to live inside of fill1 as well. Okay. All right, so that just formally unravels where dx over x has to go in such an isomorphism. So what does this mean? So T has to have the following properties. First of all, the Galois invariance means that so T belonging to that space means exactly this pair of properties. For all G in GQP, G of T should be the cyclotomic character applied to G times T. That's all it means. Okay. And then the property that it's in fill1 means that theta of T should be 0. Okay. So we're looking for an element inside of B de Rham which has this property. In fact, it's in B de Rham plus since it lives in fill 0, after all. So what is it? So how do we even construct elements of B de Rham plus? Well, we've already given one important example of an element here, which comes from roots of unity. So we have this element, which I called epsilon from last time. And this lives in OC tilt, or E or R or whatever. So when you take the Teichmuller representative of this, you get something in the Witt vectors here. And what can I tell you about it? Well, apropos of the first property here, G of this guy, well, G knows how to act on roots of unity. It acts always through the cyclotomic character. So it's like you get epsilon to the power of chi of G. Oh, I didn't say it, but chi is the cyclotomic character. Did I not say it? Okay. Right. So G has this, well, yeah, it doesn't quite have this property. The chi of G is on the main line rather than the exponent. And also theta of this element ends up being 1. That's what we figured last time as well. All right, so what we want to do is put this chi of G on the main line and turn this 1 into a 0. What should we do? We should take a logarithm. So that's what this element T is. Okay. All right, so let's let T, okay. So let T be, oh, I don't need the sub P. It's really just the power series. So one has to convince oneself that the following series converges in B de Rham plus. So it's just going to be, see if I can remember this from calculus. Right? Good. All right, so theta, so epsilon minus 1 is in the kernel of theta. So we have some power series who's in a variable which lies in the kernel of theta. So this does indeed converge in B de Rham plus, and it has the appropriate properties. So then T has these properties above. So that's why T is the analogy of 2 pi I. It's the period, the sole period of the multiplicative group. So that's what this T is doing. So it's very important in the theory. Okay. Okay. Questions so far? All right. All right. So what Faltings actually proves is the following comparison isomorphism. So if we have we define a functor d de Rham, where you input v and you output, well, it's always the same thing. You tensor with b de Rham, the period ring, and you take Galois invariance. Okay, so we have a notion of v being d de Rham. It's defined the same way. The dimension of this guy should be the same as the dimension you started with. And then the theorem of Fontaine, well, it's conjectured by Fontaine, but proved by Faltings, is that d de Rham of the cohomology of X, a smooth proper variety over QP, ends up being the de Rham cohomology. As a vector space over QP with its filtration. Okay. All right. Okay, so as far as geometry goes, this is very satisfying because it means you can read off all of the, well, yeah, it means many things. But one of them is that the information of the Galois representation here contains quite a lot of information. It contains, for instance, the Betti numbers, because the graded pieces of this filtered vector space all have dimension, which just reads off those, you call them Betti numbers or Hodge numbers? Hodge numbers, right? The individual HPQs. Yeah. Okay. Right. Okay. So for geometers, this is very interesting. But if you're just interested in QP representations of the Galois group of QP, it's still not quite satisfying because we have some functor which lands in the category of filtered QP vector spaces. And that's, again, definitely not rich enough to capture that much more information about V. So this functor is definitely not fully faithful, for instance. Okay, so what can we do? Maybe we want some functor which will be an equivalence of categories. So from that, we have to pass to a narrower class of representations and pass to a different period ring. And that period ring is the crystalline period ring. Okay, So, yeah, okay. All right. All right. So let's talk about the ring B. Chris. That will be the last one. There are others, but I will just talk about these three. Okay. So the idea here is that instead of just a filtration, perhaps this functor, this d star whatever, d sub whatever, it should have a Frobenius on it. Frobenius action. And just to make this idea plausible, let's recall the following fact about elliptic curves. Let's say E over QP is an elliptic curve with good reduction. And I consider the cohomology with L-adic coefficients, not p-adic, but L-adic. Now, okay. This is just the inverse, the dual to the Tate module, which is L-adic. And it has a Galois action. But by the criterion of Neuron Ag Shafarevich, since E has good reduction, the action of Galois just factors to the action of the Galois group of the residue field. That is, it's unramified. Oh. It's GFP, I guess. So Frobenius knows all. So, I mean, the action of Galois just factors to the action of Frobenius. And if you know what Frobenius is as a matrix on this guy, then you know what this representation is. So it's determined by Frobenius. And in fact, you actually get, just the matrix of Frobenius determines what E is up to isogeny. So, so that's good. In this situation, though, where this L is replaced by a P, I meant for L not to be P in this example, of course. We want some device which captures the behavior of a good reduction elliptic curve. The cohomology, well, it won't be unramified anymore if that L is replaced by a P. But what do we have? Well, instead, what we have, if you have an elliptic curve over a finite field, say, it has a Dieudonné module attached to its p-divisible group, and to that p-divisible group, there is attached an isocrystal. Okay. So, well, how should I explain? All right. So this is an observation of Grothendieck, which is that this more interesting guy, as a representation of GQP, is determined by well, one thing is the p-divisible group, and a stand-in for that is the Dieudonné module. All right, D attached to this p-divisible group. This is the same thing as the crystalline cohomology, E Chris of E over ZP. And the other piece of data is the filtration. What? Yeah, so the general thing is that if you have, it should really be this special fiber here over ZP. I don't really like that notation because it seems to imply that this lives over ZP, but it doesn't. But anyway. And the other thing is a filtration on H1 de Rham of E over QP. Okay, you don't need to know what all of these things are, the Dieudonné module. I just want to tell you that Grothendieck had observed that for an elliptic curve or an abelian variety, the Galois representation on H1 was determined by two pieces of data. One of them was a Dieudonné module, which has a Frobenius on it. Let's write that. And the other was a filtration. So the Frobenius and the filtration somehow determine the Galois representation over here. So Grothendieck wondered if there was some way to pass directly from this piece of data to this piece without the intermediate step of p-divisible groups. So he called such a thing a mysterious functor. Okay. So it was Fontaine who discovered how you might pass from Galois representations to objects which have a Frobenius and a filtration, and that is the crystalline period ring. Okay. So what sorts of data do we want on our crystalline period ring? So, okay, so whatever B Chris is, so again, it's going to be a QP vector space. It's definitely going to have a GQP action such that the GQP invariants are just QP. It should have a Frobenius. And finally, it should have a filtration, just like B de Rham did. Okay. Descending filtration. Okay. All right. Now, the construction of the thing is a little bit strange. I mean, it's hard to motivate without a discussion of crystalline cohomology, which involves divided powers and such. And I've only got 12 minutes, so this is kind of a saved by the bell situation. So let's try to, I can certainly define the thing. So it definitely starts with W, the ring of Witt vectors of OC tilt. And, okay, so this again has a map, which I call theta, to OC like this. And I'll tell you that W of OC tilt is contained inside of our ring B Chris, but in fact it's contained in a smaller ring, which is A Chris. This also maps to OC. And I'll just tell you about the properties of this thing. So, okay, so A Chris is p-adically complete. And this map is continuous. And furthermore, A Chris has this funny thing called divided powers. Oh, I should also say it's p-adically complete and flat as a ZP algebra. Okay. And also, the ideal, which I'll call I, which is the kernel of the map theta from A Chris to OCP, has what's known as divided powers. All right, what does this mean? So whenever x is an I, well, x to the n divided by n factorial has to also be an I. All right, that's the condition. Well, it's a funny condition without some sort of motivation. But, all right. Yeah. The best I can say is that in this subject, yeah, okay, when you consider de Rham complexes, you want them to be exact as sheaves. So this requires a Poincare lemma, and that requires you to be able to integrate differential forms, at least locally. And that sometimes requires, that integration process requires denominators, and denominators take forms like this. Okay. All right. Okay. So, right, so I've told you what A Chris is. Well, I defined two more rings. As Gabrielle said, there's infinitely many rings you could take. So B Chris plus is the ring you get when you take A Chris and you invert P. And B Chris is the ring you get when you take B Chris plus and you invert the element T, because T belongs to A Chris as well. That series that defines the logarithm also converges inside of A Chris. One must check. Okay. All right. So this has all of the necessary structures. It turns out that the Frobenius map phi from, well, certainly OC tilt has a Frobenius automorphism because it's a perfect ring. That automorphism extends to an automorphism of the ring of Witt vectors. And that automorphism extends to B Chris. Okay. So it has the Frobenius. And does it have a filtration? Yeah, it's the filtration given by the ideal T. T to the n B Chris plus. That's the nth step in the filtration. Okay. All right. All right, so that's what the crystalline period ring is. It contains the p-adic periods for all varieties over QP with good reduction. All right. All right, so final comparison theorem here. So, well, it's like this. If x over zp, say, is smooth and proper, then d Chris of the étale cohomology is going to be, well, yeah, okay. So it's going to be like the crystalline cohomology of this. Yeah, okay. ZP. Yeah, I do better invert P. So, I mean, I have not really defined what this HN Chris is, but it's some object which has both of these properties, this Frobenius action and this filtration. Okay. Right. All right, so this is sort of grand comparison theorem is due to Fontaine, Messing, Falting, Tsuji, Niziel, Bott. Did I forget anyone? Okay. Right. Okay, but I actually promised more than this. I mean, I wanted some functor, which is going to be our d Chris, which gives an equivalence of categories, and not just a functor into some weak category of linear algebra. So, so this is the theorem of Comez-Fontaine. Which is that d Chris is an equivalence of categories from crystalline representations of GQP, which are the ones for which this d Chris has the right dimension, to, well, okay, what are known as weakly admissible filtered isocrystals. Okay. That says weakly admissible filtered isocrystals, which we can take apart one by one. So isocrystal, so it was mentioned in Gabriel's last talk. In this case, it's just going to be a vector space over QP together with this Frobenius map phi. The filtered part is clear. The weakly admissible part is some rather technical assumption. I'll just say this. The weakly admissible means that the Newton polygon lies above the Hodge polygon for all subobjects.
It implies that, or that's the whole definition?
That's the definition of weakly. That says WA. That's weakly admissible. Okay, so this category of filtered isocrystals are linear algebra objects. They're QP vector spaces with two structures on them. A Frobenius, that's what the isocrystal means, and a filtration, that's what filtered means. And this admissibility criterion is a kind of compatibility. Yeah.
Equality for the group, like equal endpoints.
Oh, okay. Yes.
Because if you mention dimension one,
Oh, I see. Right, with the same endpoints?
if it's the full,
If it's the full thing? What do you mean?
if the subobject is the whole.
Oh, if the subject, I see. You need one more condition for weak admissibility?
Because if you imagine a one-dimensional object,
Oh, being really far apart. I see. You're absolutely right. Okay. I see. Okay, so with the same endpoints for the whole object. I'll just write this. Same endpoints for V itself. Yeah, okay. Yeah, I see what you're saying. All right. All right. The Hodge polygon has something to do with the filtration. I mean, it's just a polygon that you draw on the plane where the data that you put into it is just the dimensions of the filtered pieces. That's all. The Newton polygon is something else. It has to do with the eigenvalues of Frobenius. The eigenvalues of Frobenius lie in some extension inside of QP bar, and you look at their valuations, and those valuations enter into the Newton polygon. So this just is some relationship between those two sets of data. Okay. All right, so this is an equivalence of categories. And so this is pretty satisfying, and it also relates to geometry. So with a few minutes left, well, I could do that example, or I could draw this like big Venn diagram thing. We'll do the Venn diagram thing. Okay. All right. So just to clarify what has happened over the last 2 lectures. So p-adic representations, well, one rarely deals with them in any explicit manner, as in this is what the matrix attached to any given automorphism is. Instead, one attaches certain linear algebra objects to them. And in yesterday's talks, we learned that there was an equivalence between all GQP representations and phi gamma modules, étal phi gamma modules. Yeah. Okay. And then in today's talk, we talked about 3 subclasses of this. The representations which are Hodge-Tate, and B Hodge-Tate was a map from this to just graded QP vector spaces. Inside of here are the representations which are de Rham, and B de Rham maps those into filtered QP vector spaces. Of course, there's a map this way, which is just to any filtered QP vector space, take their associated graded. And then inside of this are the representations which are crystalline. And there's actually an equivalence between this and the weakly admissible filtered isocrystals. Okay, so the biggest leap is from here to here. There are so many GQP representations, and very few of them are Hodge-Tate. So, for instance, you could take a cyclotomic character and raise it to some power which is not integral, and then you get something which is not Hodge-Tate. These correspond to some class of phi gamma modules. Phi gamma modules, it's a very satisfying thing because it's an equivalence, but these are quite complicated. They're much more complicated than these guys, say. And then as far as the geometry goes, you get a de Rham representation whenever you consider Hn of xqp with p-adic coefficients. So étal cohomology gives you lots of examples of de Rham representations. When do you get crystalline representations? You get them when x has good reduction. So when you sort of, in your mind, think de Rham comes from kind of anything in geometry, whereas crystalline comes from x having good reduction. Ooh. That is, you can find a smooth proper model of x over ZP. I didn't talk about various shades in between here. There's potentially semi-stable, which is just de Rham, turns out. There's semi-stable. There's crystalline. What am I forgetting? No. Okay. This concludes my talk on p-adic representations. Hope you enjoyed. Okay.